Hello friends, welcome to lecture 8.4 in the unit on DWT. In this lecture, we are going to particularly look at different wavelets and scaling functions and study the properties of wavelets that are relevant to DWT. So, all this is in the context of DWT. We had done this exercise earlier for CWT. So, now it is the turn of DWT, and also we will learn how to compute the scaling and wavelet functions from filter coefficients. Remember, we have said that as far as computation of DWT is concerned, both decomposition and reconstruction, one does not need the scaling functions or the wavelets, but still it is a useful exercise to learn how to derive these functions, how do they look like, what do these basis functions look like, because what we need to do eventually is to select a wavelet for a particular analysis or a scaling function, and in selecting a particular family of wavelets we would like to know what features these basis functions have, and unless we look at these functions in time, that is their shapes, we will not be able to make much of a decision. Now, having said that, all the properties of wavelets or scaling functions pretty much can be derived from the filter coefficients without actually computing the scaling or the wavelet functions themselves. Okay. So, let us begin our journey. Just to recall, although I say here the title of the slide is scaling functions for DWT, it also means that we are going to look at we are looking at wavelets as well. Now, as in CWT, the wavelets should satisfy the 0 average condition. So, this is just to recap the basic conditions that any wavelet for DWT should satisfy. It should have 0 average, and of course, the existence of scaling functions for DWT is very important, and the prime requirement for the existence of a scaling function is that the wavelet should have a finite admissibility constant. But additionally, what we require in DWT is that the scaling function and its integer translates should constitute a basis, and preferably an orthonormal basis for some subspace of finite energy signals in the real space. All right. So, I hope it is clear. As far as CWT is concerned, a scaling function exists as long as the admissibility constant exists, but for DWT the set of admissible scaling functions are those whose integer translates constitute a basis for some subspace of finite energy signals, and this basis preferably should be orthonormal. Why should we seek orthonormal basis functions? Well, as we have learned in the previous lecture, orthonormality gives us computational efficiency, nice expressions for reconstruction and so on. So, that is the reason essentially, right. Now, as far as the different wavelets for DWT are concerned, and let me also help you recall the fact that when we select wavelets in DWT, we normally select the scaling function. In fact, we select the low pass filter. We do not really directly select the wavelet necessarily, but one can do that as well. Eventually, we use both the scaling functions and the wavelets. So, it is therefore justified to begin our discussion to talk about the wavelets for DWT, and we will shortly see that whatever requirements I want on the wavelet actually translate to the constraints on filter coefficients. We have seen that already in the last lecture, but I am going to explicitly state those constraints here. Now, if you recall the lecture on CWT, where we discussed the different wavelets for CWT, we said there are many types of wavelets. There are real valued, there are complex valued, and then there is a classification based on orthogonality, biorthogonality and so on. In CWT, we restricted our discussion to only real and complex valued CWTs, wavelets. Here, when it comes to DWT, we are going to primarily use real valued wavelets, but those that are orthogonal or biorthogonal or sometimes non-orthogonal. So, let us look at these terms briefly. We know already what orthogonal wavelets are. What we mean by orthogonal wavelets is that wavelet at any scale 2 power m, because we are looking at dyadic scales, and its integer translates should be orthogonal to the scaling function basis at that scale. So, if I take any scale or any level m, then I have a set of wavelets at that scale and their integer translates. They should be orthogonal to the phi of t at that scale. So, phi of m comma n at t. So, this is essentially saying using the notation that we introduced in the previous lecture, Wj subspace should be orthogonal to the Vj subspace. Wj is the space of Wm is the space of details at scale 2 power m, and Vm is the space of approximations at level m or at scale 2 power m. Wm should be orthogonal to Vm, that is what we mean here. And once that condition is imposed, as we have seen in the previous lecture, it amounts to saying that wavelets themselves are orthogonal at that scale, that is the translates of wavelets and the wavelets are orthogonal. Now, this condition can be restated in terms of the filters. Essentially, we want the filters to be orthogonal. What do we mean by orthogonal filters? Well, the inner product of the low pass and the high pass filters should be 0. So, let us take the example of a Haar wavelet. So, we know for the Haar wavelet or the Haar scaling function, we know that the low pass filter associated with this phi of t is of length 2 and the coefficients are 1 over root 2, 1 over root 2, and the high pass filter associated with the wavelet is again of the same length, and we know how to derive g from here, because the Haar wavelet is orthogonal to the scaling function at any scale. You can use the result that we gave in the previous lecture. You can verify that g of n is minus 1 raised to 1 minus n h of n. So, you can verify that g is indeed this here, and n of course begins from 1 here. So, if I set n equals 1, then I get g 1 to be 1 over root 2, and if I set n equals 2, then I get minus 1 over root 2. So, you can quickly see here that the inner product between these two sequences is 0, and this amounts to saying that the wavelet is orthogonal to the scaling function at that scale, or at any scale in fact. Although we write this at the level m equals 0, this is also true at any scale. For all n, that is at a fixed m, for all n this is true. That is what we mean by orthogonality here. In terms of the subspaces, we say that Vm is orthogonal to Wm. Psi m comma n spans the subspace Wm, and phi m comma n spans the subspace Vm. In addition, we have seen in the previous lecture, when orthogonality is satisfied by the wavelets and scaling functions or by the filters, then the synthesis filters are also identical to the decomposition filters. So, that is naturally guaranteed. And orthogonality essentially means that the family of wavelets, that is, now if you look at the entire set of wavelets, not just at one scale, but at all scales and their integer translates put together, it constitutes this family constitutes an orthogonal basis for L2R. So, let me again show that to you schematically. So, what we have from MRA is that these scaling functions and wavelets are spanning a set of embedded or nested spaces. So, if you recall the diagram that we drew earlier, that is in the previous lecture, then if we call this as V naught, then V naught is spanned by phi of t, and then you have V1, and then you have V2 and so on, and of course V naught itself is contained in V minus 1. So, the subscripts are pertaining to the referring to the value of m essentially, and this is V2. What the difference between V2 and V1, that is this space here is W2 and this is W1 and so on. So, if I had a V3 here, then I would have W3. Now, you can see quickly that V3, V2, V1, V0, V subscript minus 1 and so on, they are all inclusive. So, the basis functions responsible for these approximation subspaces, they are not independent, because one is contained in the other, right. If I look at the basis functions for all the subspaces V minus 1, V0, V1, V2, V3 and so on. In other words, if I look at phi m comma n of t for all m n in the integer set, this family of scaling functions cannot be a basis for the real number space. Definitely when you look at all these the union of V3, V2, V1, V0, V minus 1 and so on, if you look at the union of Vm as m runs from minus infinity to infinity, that is definitely the space of finite energy signals, that there is no doubt about. But what is not true, or what is not true is that this is a basis for L2R. This cannot be, because one of the prime requirements of basis is that they should be independent. On the other hand, if you look at W3, W2, W1 and then W0 and W minus 1 and so on, they are all exclusive, right. That means the basis functions responsible for V2 are in fact orthogonal, or they are independent of the basis functions in W3 and W1 and W0 and so on. So, each what are the basis functions for W3, W2 or W3 and W1 and so on, they are the wavelets at that scale and that integer translates. Therefore, the basis functions here that span the detailed spaces as m runs from minus infinity to infinity, they can constitute a basis for the space of finite energy real signals. In other words, here if I look at psi m n of t, again m and n over the integer set, they can form a basis. What kind of basis? Orthonormal basis. They are not only orthonormal within a subspace W2, but they are also orthogonal across subspaces. That is what this means. That is a very important point, whereas for the scaling functions that is not true. The scaling functions are orthonormal only within a subspace, but if I look at the scaling function in for V1 and V2, they are not mutually orthogonal. So, when we impose the requirement that the scaling function should be orthogonal or orthonormal, we only impose it at a specific scale. We do not impose orthonormality across scales. That is a point. Whereas with wavelets, that is not the case. They are not only orthonormal at a scale, that is when we say they, the wavelet and its integer translates. That is, at any scale, the wavelet family is this 2 to the minus m by 2 times 2 times psi of 2 to the minus mt minus n. So, for all values of n, that is what we mean by they. They are orthonormal at a given m and across m as well. That is the beauty of these wavelets. And like we said here, the union of all the approximation subspaces is L2R, which is the space of finite energy real signals. The union of all W's is also L2R. That is, I can in principle only look at the approximation spaces or the detail spaces, but as far as the basis is concerned, this does not constitute a basis, whereas this constitutes a basis, in fact orthonormal basis. So, that makes a big difference, and that is why a lot of discussions begin with wavelets rather than with scaling functions. But in DWT, because we are interested in approximations, in practice I am interested in approximations, I want to construct approximations, and the discussion therefore begins from approximations. But as far as basis is concerned, wavelets are the basis functions for L2R. Of course, as we mentioned earlier, when I have orthogonal wavelets, I have the privilege of luxury of computational efficiency and compact representations of signal. Compact meaning with as few coefficients as possible. Remember, coefficients are the inner products between the signals and the basis functions. Moving to biorthogonal wavelets, which we did not discuss in detail in the previous lecture, but I did mention this term when we were talking about synthesis filters after we discussed the decomposition filters. Remember, we imposed orthogonality at the time of designing the decomposing filters themselves. That is, we said Wm is should be perpendicular to Vm. But suppose I do not do that. Suppose I say I want a set of wavelets that span the detail space, and I already have a set of scaling functions that span the approximation space at any scale, and I do not impose orthogonality there, but just have some wavelets that satisfy the condition that they should span the detail subspace, and then look at the synthesis, that is when I turn to the reconstruction. At that time I require that the synthesis wavelet filter should be orthogonal to the analysis scaling function. All right. So, let me again show what I mean by that. Just as we have here approximation and detail spaces spanned by the scaling functions and wavelets, let us call them decomposition filters. I can also have spaces spanned by the synthesis scaling functions and synthesis wavelets. We have used this before, we have mentioned that in CWT as well. I can use a different synthesis function that is different from the analyzing function. Likewise, here I can use a scaling function for synthesis that is different from the analysis function. Now, just as we developed this entire theory based on phi of t and psi of t, I can also have approximation spaces based on phi tilde of t and detail spaces based on psi tilde of t. They are essentially duals. So, it is not that only phi of t and psi of t can generate these spaces, they are also capable of generating these spaces. If you use a notation now that the subspace spanned by phi tilde m of t minus n, where n is some integer set, let us say this spans Vm tilde and likewise the set of wavelet functions, but the synthesis wavelet functions and their integer translates span Wm tilde, then we arrive at biorthogonal wavelets by requiring that Wm tilde be orthogonal to Vm and Vm tilde be perpendicular or orthogonal to Wm. So, this is different from what we see in orthogonal wavelets, where we require Wm and Vm to be orthogonal. In this here it is a biorthogonal. So, you see that Wm is not perpendicular to Vm, but it is perpendicular to the approximation space generated by the synthesis wavelet functions. Now, on the face of it, it sounds a bit weird as to what does this make, what does this mean? Well, what this means is that there is a certain symmetricity here in the reconstruction and the decomposition, and in fact this symmetricity here gives rise to what are known as symmetric wavelet filters. You can show that orthogonal filters can hardly be symmetric. Yeah, you can design symmetric orthogonal filters. What do we mean by symmetry? Well, when I look at the scaling function, for example, the Dobeschi scaling function, it looks like this, for example, qualitatively. So, this is how a Dobeschi scaling function would look like, all right, of some order. Now, this Dobeschi wavelet scaling function is an orthogonal scaling function, that is, belongs to the family. Corresponding to this is a wavelet which is orthogonal wavelet. Dobeschi wavelets are not biorthogonal wavelets. Now, you can see that this scaling function is not symmetric. In fact, the associated wavelet is also not symmetric. So, what happens if there is no symmetricity? Remember, I am using wavelets as filters, and whenever I perform filtering, whenever I filter a signal, the phase of the signal is altered. And when I use filters whose impulse responses are not symmetric, although I do not show impulse response here, but phi of t is the impulse response of the associated low pass filter. When that is not symmetric, then phase distortion occurs, and when phase distortion occurs, the sharp changes or the edges in the signal are distorted, and that is not really good for signal analysis in certain applications. I want therefore symmetric wavelets and scaling functions with as minimum width as possible, because if I have larger and larger width, what happens is the time resolution of the wavelet, the mother wave itself will be poor. Remember, ultimately we are looking at time frequency analysis. With orthogonal wavelets, to design a near symmetric wavelet, you require a much larger support in time, and as a result also much larger number of vanishing moments, as we shall learn later, and therefore you have to sacrifice on the that is, you have to get a more smooth wavelet and so on. Whereas with biorthogonal wavelets, you can nicely design symmetric wavelets. In fact, there is a whole lot of literature. I will direct you to a book, textbook, which discusses all applications of different wavelets to different processes, and in that textbook you will see that biorthogonal wavelets are very good for texture classification, image analysis and so on, where orthogonal wavelets will generate a lot more coefficients. Remember, ultimately one of the main applications of DWT is signal compression, and in signal compression we are seeking wavelets that can represent a given signal in as few coefficients as possible. With biorthogonal wavelets, you can achieve this in a much better manner in many applications than orthogonal wavelets. That is because again of the symmetry and the flexibility that you have given. Orthogonality is a very tight requirement, okay, but it is useful in its own way. One of the examples of biorthogonal wavelets are the biorthogonal spline wavelets. I am not showing you any wavelet shapes here per se. We will do that when we look at the MATLAB session. At this moment, you may be wondering why we are not looking at any graphs or any profiles of the functions of the wavelets, but I would like to reserve that for the MATLAB session and show you how you yourself can plot these wavelet functions and look at them. I have already shown glimpses of that in CWT. Now, finally, we have non-orthogonal wavelets. Now, these wavelets are also popular for one reason. That reason is when I use orthogonal wavelets, which are used widely for signal estimation and signal compression, despite having many advantages, one of the key disadvantages of orthogonal disadvantages of the orthogonal wavelets is that it is not shift invariant or translation invariant. What do we mean by that? Well, if there is a feature in the signal, let us say it is a biomedical signal or a signal coming from a vibration machinery and so on, there are certain features of interest to me, and I would like to keep track of how these features are shifting in time. And if you recall, the way we are computing the dyadic DWT and then the orthogonal DWT, basically what we are doing is we are evaluating CWT at specific scales and also translating at specific translations only, right. That is we are translating in such a way that we generate non overlapping basis functions, and that results in minimal representation. But then what happens is, if there is a feature that has shifted in time, all right, the same feature appears again at a later time, and this shift in time for the feature, if that is not commensurate with the shift of the wavelet functions that you are using, then you will lose out on that feature. That is, this feature is not the shift of the feature in the signal, it could be a sudden change or whatever, is not correctly captured by the DWT. That is because you are taking time steps in a particular manner that is much different from the sampling interval of the signal. So, to overcome that property, so that disadvantage, what one does is only discretizes the scales and translates, that is chooses a translation parameter equal to the sampling interval, that is chooses to march ahead in time which is equal to the sampling interval. The tau parameter that we had in CWT is now no longer going to be n times 2 power m. It is going to be simply n, where n will be equal to the sampling instant itself, which means I will still choose dyadic scales. That is not the reason that I am missing out on the translation invariance. The scales has got nothing to do with it. The reason why I was not able to detect a shift of the feature in time is because I was taking steps proportional to the scale of the wavelets. But now I am going to relax that, and I am going to let myself let this wavelet move not proportional to the width of the scale, but in steps of sampling interval. There, as a result, if there is a feature that has shifted in time, I can easily capture that feature correctly, okay. And that leads to what is known as shift invariant DWT or maximal overlap DWT. Why do we have a maximal overlap here? Because in time I am marching ahead one sampling interval at a time. Obviously, the disadvantage of that would be the loss of computational efficiency. I have to compute a lot more coefficients than necessary. As a result, we get redundant representation of the signal and so on. But this redundancy and the loss of computational efficiency come with an advantage that I will be able to detect shifts in the features. Now, clearly the moment I have wavelets that are not shifting in time proportional to the scale, but rather proportional to the sampling interval, I am going to generate a set of overlapping wavelets. So, let me just show that to you on the graph. So, let us say I have some signal here, and what I am doing in let us pick a wavelet here which is located at this point. So, this is some wavelet which is located at the origin at some scale. In DWT, what I do is the next wavelet that would analyze the signal would begin from here, and the center would be placed here, right. Again, of course, I am choosing I am drawing it in very qualitative manner, just but hope you get the point, right. So, it is going to be of the same width here and so on. So, this is n equals 0, n equals 1 at that scale and so on. This is how I am going to march ahead in time. Whereas, in maximal overlap DWT, the next wavelet, suppose this is the sampling interval here and so on, the next wavelet is going to be located, it is just going to be shifted in time this way. All right. That is how it is going to shift in time. As you can see, this wavelet here, shifted wavelet, and this wavelet here are highly overlapping. In fact, it is maximal overlap. Whereas, with the DWT, that is a classical DWT, orthogonal DWT, there is there is no overlap between this wavelet, the shifted wavelet and this, but this big shift that I have taken could miss out a feature that would have shifted in time much less than the shift that you have taken at that scale. That is the step that you have taken at that scale. If there was a feature here in the signal somewhere here, and at a later time the same feature appeared here, because you have taken this step here in classical DWT, you would miss capturing this shift, and that is the main problem with the classical DWT. On the other hand, because of the lack of overlap, you have computational efficiency, you have minimum representation and so on. So, that I hope now you understand what is the difference between a shift invariant DWT and the classical DWT. A lot of this is discussed in the book by Percival and Walden, and I will give you a bunch of references in the closing lecture, but yeah, you can just go and read. The book is titled Wavelets for Time Series Analysis.